Welcome to Chapter 7. I'm Dr. Ala Jabbar Al-Maliki, and today we are breaking down the mechanics of sorting, a foundational operation in your data structures course. Sorting is the process of arranging data into a specific order, such as the ascending sequence you see here. In this session, we will define these techniques, implement them in C++, and analyze the time complexity you'll need to master for your exams. These 5 algorithms are the engines behind real-world systems. They allow databases to track student IDs, search engines to rank results, and e-commerce sites to organize products by price instantly. Raw data is difficult to process at scale. Sorting provides the structure that makes information searchable and useful for complex computing tasks. Insertion sort works by taking one element at a time and placing it into the correct position, like organizing playing cards. It is highly efficient for nearly sorted data, achieving an O of n best-case speed, but randomized data forces a worst-case O of n squared complexity. Selection sort takes a different approach. It scans the entire unsorted section to find the absolute minimum value and swaps it directly to its final position. Because it requires a full scan regardless of initial order, all cases are consistently O of n squared. These intuitive algorithms are straightforward to code, but the high number of scans and shifts required makes them inefficient as datasets grow larger. Shell sort groups elements separated by a specific gap. Starting with a gap of 4, the gap sequentially reduces to 2, then 1. This early long-distance movement significantly reduces shifts, achieving an O of n log n best-case speed, making it highly effective for medium-sized datasets. Recursive algorithms like merge sort use a divide-and-conquer strategy, continuously halving the array into individual blocks. During the merge phase, the blocks combine in sorted order, but the L and R pointers in the C++ code require O of n extra memory for temporary arrays. Quicksort selects a pivot, here 5, and partitions the array. Pause and write down the array's state. It should now look like this, with 5 correctly positioned. However, if a poor pivot is selected, the algorithm slows down to O of n squared. By dividing data into smaller segments, recursive algorithms maintain much faster performance as data scales, though they require balancing extra memory usage against the stability of your pivot selection. This matrix summarizes when to deploy each tool. Use insertion sort for small data, shell sort for medium data, merge sort for large stable datasets, and quicksort for fast general-purpose sorting. To succeed in your exams, avoid these common traps. Never forget that merge sort requires extra memory, and always double-check your recursive logic in quicksort to avoid poor pivot selections. Mastery of sorting means knowing exactly which algorithm will make a system faster. Practice these C++ implementations, and I will see you in the next chapter.